Good morning, everyone. My name is Jay,
My name's Keneni.
and today we're presenting on our research project from the summer that we did alongside Dr. Kaylee Condit and Dr. Kevin Mahan on Monazite geochronology from the Halvorin Creek Shear Zone in southwest Montana. So just as a little bit of an introduction, our main focus this summer was trying to construct a timeline of metamorphic and tectonic events in and around the Halvorin Creek Shear Zone. And we did this primarily through the use of geochemical analysis and radiometric dating of monazite, which is a metamorphic mineral that's found in rocks in that general area. So we had a couple key questions when we were going into our project. They're not the only things we found answers to, but they were the main focus going in. So one, since we're building a timeline, the big question is, are there any trends in the mineral ages that could help us constrain specific timing of metamorphism? Two, if there are any trends, are they the same inside the shear zone and outside, or are they different? And three, do the mineral dates in the shear zone support the hypothesis that it developed during the Big Sky orogeny, which occurred about 1800 to 1700 million years ago?
Yeah, and just for a little context about the area, the Halvorin Creek Shear Zone is located within something called the Wyoming province or Wyoming Craton. And the whole area and a lot of the timing that we found that was connected to the formation of the shear zone was due to this Big Sky orogeny event, which made the Northern Madison Range. So if you look at the figure to the right, you can see this large on the A figure at the bottom, where you can see this Big Sky orogeny event where the Wyoming province collided with the Medicine Hat Block structure. Here. Yeah, so is that, hopefully everyone can hear a little bit better, but yeah, where it collided with the Wyoming Craton and the Medicine Hat Block and made this northern Madison Range and the Halvorin Creek Shear Zone, which you can see in figure B. Yeah, and it's suspected that most of the deformation and the local deformation is due to the Halvorin Creek Shear Zone, which you can see on the top figure. And there's two structures, like on the left and the right, the Bear Basin Block, which was also researched, and the Moon Hat Block, which is towards the bottom, which was included in the research that we did this summer, along with samples directly within the shear zone. And as for some of the methods, we were looking at thin section and photomicrograph images to help contextualize some of the composition within some of the samples. So you could see like the individual grains of different minerals within these rocks, these high grade metamorphic rocks. So as you can see in the figure to the right, you can see the foliations within the rock, and on the bottom, where it's a polarized image, you can see a lot more of like the boundaries of individual minerals and other stuff within the rock. And this was all taken on something called an electron microprobe, where we were able to get these high spatial resolution images. Yeah, and help just get a better idea of the composition of these rocks.
Yeah, and so once we were done with kind of the qualitative analysis, looking at the composition and figuring out how to classify our data, we then looked at the radiometric dating for each of the domains that we isolated. So radiometric dating is basically when you take the ratio of the radioactive material in a sample, so in this case uranium and thorium, and you compare it to whatever their decay products are. In this case, both uranium and thorium decay into lead. So since we know basically the standard decay rate of both uranium and thorium, and we know the amounts of both uranium and thorium and lead in the material, we can use that to figure out what the dates are for those materials. But it is important to note that the only reason this works for this particular type of radiometric dating in this case is because monazite doesn't incorporate common lead into its structure when it's forming. So it doesn't take in lead from its environment. So we can be confident that anything that's inside of it is from this decay process. So there are also a few specific reasons why monazite was chosen for this study. Most people who are even vaguely familiar with the idea of geochronology are more familiar with zircon. So anytime you see like a big news article that's talking about like, we just found the next oldest material on the planet Earth, they're usually talking about dating that was done with zircon. But monazite is also used in a similar way. And in this case, we specifically chose monazite for a couple of reasons. So the most important is availability. Monazite is a very common metamorphic accessory mineral, and it can be found in both igneous and sedimentary based metamorphic rocks. So we were looking at samples from both granite and quartzite, so igneous and sedimentary. So it was really important we use something we could find in both. It's also very durable. So we're looking at rocks that at one time were as deep as possibly 40 to 45 kilometers into the crust, which is very hot, very intense pressure. You need something that is going to maintain the data you need when you're doing your analysis. And monazite has a very high lead closure temperature. So that means as long as the monazite stays under that temperature, the lead will stay inside of it. It won't diffuse out into the environment. So as long as it stays under that temperature, you can be very confident that it has all of the information you need. And since the temperature is so high, there's a pretty good chance that it never diffused any of that lead out. And then finally, it is also very efficient for what we were doing. So one of the cool things about monazite is it likes to grow in layers. So you can kind of see that on some of the geochemical maps right here. If you look at that very center picture there, you can see that the center of the grain is very dark. And so what that's telling us in this case is it has very low uranium content. And since it's pretty homogeneous, we can assume it all grew at the same time. And so that whole area will have the same age. But then something happened and it stopped growing for whatever reason. And then conditions changed again and it started regrowing or recrystallizing along the edge. So you have that really high uranium outer edge, which is going to have a different age. And so by looking at these kinds of relationships, you can kind of determine which parts are going to be different ages and then find out the dates of multiple events that happen in the area using a single grain. So what we're looking at here is the results that I got from my analysis of the Moon Lake block samples this summer. So that was what I was working on. The data is separated a few different ways. So the colors are just to show which sample it's from. And then it might be hard to see on your screen, but the shapes of the different points is to show what kind of domain it is. So we were looking at rims, cores, and whole grains for dates. And then so all of the stuff at the top is going to be the oldest, and all of the stuff at the bottom is going to be the youngest. And what we found from this, and what you can probably see really easily looking at this plot, is that everything's separated into about 2 main time frames for formation. So we have one older kind of like edge of the Neo-Archean time frame, is about 2570 to 2470 million years old, and then a younger population, which is about middle of the Proterozoic, and that's about 1770 to 1730 million years old. Another thing that came out of this, for the Moon Lake block at least, is that most of the material is much older. So most of it is in that Neo-Archean time frame, and whereas only a third of the material is in that younger Proterozoic time frame.
And the samples that I was working on this summer were within the Hellroaring Creek shear zone. And as you can see from the graph, there are a lot more domains in my samples that were in that younger time frame. So that 1.7 to 1.7 billion years old, and only like about 4 of the domains registered in that much older time frame. Yeah, and a lot of the older domains that were found were either whole grains that developed completely during that Neo-Archean time frame, or cores that developed a longer time ago, and then the rim developed around that big sky orogeny event that 1.7 billion years ago. And as for some of our main conclusions, there are about two main time frames of metamorphism and monazite growth that we found within both of our samples, and a slight implication for a third event, especially in the shear zone samples that we found. But it supports that the shear zone formation was about during the same time as the big sky orogeny event or slightly after, since with the geochronology, it's hard to tell smaller time frames and much easier to tell like within like billions of years. So if the shear zone developed maybe like a day or even a couple of years after the orogeny, it wouldn't show up as well within the monazite as these two main deformation events.
Yeah, and so another really interesting thing that came out of this that we weren't necessarily looking for, but it was really fascinating, is that certain populations, certain age populations showed multiple pulses of growth in small time frames. So for example, you can kind of see what I mean by that here if you look at the younger Halroyan Creek shear zone material. So the colors are representing the different types of domains. And some of those domains are actually from the same grains. So for example, when we say pulses, what that means in this case is, like we were talking about, monazite grows in layers. So you had core growth in this time frame, and then something changed and it stopped. And then something changed again and it started growing again. But it all happened in a very short time frame. And we know that this means that the conditions must have been somewhat disparate, because had they been the same and consistent all the way throughout, all you would have would most likely be just whole grains that all had the same composition. And so we saw that primarily in the young population within the shear zone, and then the old population outside of the shear zone. And then finally, to kind of tie this into the broader area, another really interesting thing that we noticed was that the old growth that dominates the Moon Lake block that we talked about doesn't really show up in Bear Basin on the other side. So previous geochronology studies have been done on monazite in Bear Basin, and it's approximately the same distance on the opposite side that Moon Lake block is on this side from the shear zone. But almost all of the material over there is from, the 1700-ish Proterozoic era, as opposed to the much older Archean material that's in the Moon Lake block. And again, from this study, we can't necessarily say what that means, but it does at least show that the shear zone serves as some kind of barrier or some kind of boundary between these two areas that have very distinct metamorphic and evolutionary histories. So that might be somewhere to like start asking questions and looking at for future studies. So in conclusion, we just wanted to thank our mentors, Dr. Kaylee Condit and Dr. Kevin Mahan and Theron Sowers, for all of their help and support this summer. We also wanted to thank Dr. Andy Ellis and all of the UNAVCO staff that made this, this whole project happen this summer. Because I don't know about anybody else, but I was really worried it wasn't going to happen. And then thank you to the National Science Foundation for their financial support, and to all of you for attending and listening today.